You ever look at a huge bridge or some complex machine and just wonder how an engineer knows it's going to work? It's like they've got this special kind of X-ray vision, right? Like they can see all the invisible forces holding the whole thing together. Well, today, we're going to learn that secret. We're going to start seeing the world like an engineer.
So what is the secret? How do they actually see the tension, the compression, all the weight that's constantly at play in, well, every single object around us? It's not magic, not at all. It's a special way of thinking, and it uses a couple of really powerful tools that let them translate the real world into something they can actually analyze.
All right, the first, and I mean the most fundamental tool in this whole toolkit, is something called the free body diagram. This is pretty much the starting line for solving almost any problem in statics. That's the science of forces that are in balance.
So what is it exactly? Well, a free body diagram, or FBD for short, is basically a super simplified sketch, and the key word here, the most important one, is isolated. You mentally just lift an object out of its environment, and then you draw only the forces from the outside world that are acting directly on it. And that simple act of isolation, that's what makes a complicated problem suddenly crystal clear.
And making one follows a few simple steps. First, you pick what you're going to analyze and you isolate it. You just draw its outline. Then, and this is the most important part, you add arrows, which we call vectors, for every single force that's touching it. We're talking pushes, pulls, its own weight, and the forces from whatever was holding it up. Then you just slap on a coordinate system and any measurements you need.
Let's put this into practice. Here's something pretty simple. A 160-pound lawn roller, and it's being pulled up a small slope. Now, just looking at it, it's not super obvious how all the forces are balancing out, right? So let's use our new tool.
And boom, this is what you get. We isolate the roller, and just like that, the whole picture becomes incredibly clear. You've got the pulling force, P, from the handle. You've got its weight, W, pulling straight down thanks to gravity. And then you've got the normal force, N, which is just the ground pushing back up against the roller. The messy, real-world scene is now a clean, simple diagram with just 3 forces.
Okay, so the lawn roller, that was a pretty easy one, but the real power of the free body diagram is how it lets us tackle situations that at first glance look just insanely complicated.
Get a load of this utility pole. It's being yanked in all these different directions by 6 power lines, and it's being held in place by one single guy wire. How in the world would you even start to calculate the tension in that one wire to make sure it's not going to snap? I mean, it just looks like a total mess of forces.
But you know the drill now. The very first step is to draw the free body diagram. We can simplify all those power lines down to just 2 main forces, and now we've got this clean, top-down view of everything acting on that pole. All that visual chaos, gone, replaced by a simple problem with a few arrows.
And that diagram isn't just a pretty picture, it's the roadmap for the math. By using the equations of equilibrium, making sure all the forces cancel each other out so the pole doesn't move, engineers can solve for that unknown tension. And the answer they get is super precise, that one wire has to handle 23.6 kilonewtons of force. That's the power of this method. It turns chaos into clarity, and clarity into a real answer.
So, the free body diagram is awesome for figuring out the forces acting on an object. But what about understanding how forces travel through an entire system? For that, we're going to need to level up.
I mean, think about something like a car engine or a giant industrial press. There are hundreds of parts, bolts, gears, frames. Drawing a free body diagram for every single little piece would be an absolute nightmare. It's just too much detail. You need a way to see the big picture. So, you gotta ask, is there a more intuitive way to do this?
Oh yes, there is. It's called the force flow concept. And instead of isolating one tiny part, you actually trace the entire journey a force takes as it travels through a machine. The best way to think about it is like a highway for loads. You're just drawing the path the force takes from start to finish.
And this right here shows you just how powerful that idea is. Here are 2 different designs for a press. By just sketching out the force flow, these red lines, you can immediately, without doing a single bit of math, tell which design is way, way better. Take a look. Can you see why? Okay, let's break down the one on the left. The force flow loop is huge, right? It travels all the way around that big outer frame. That means the entire frame is taking the load. So it has to be super heavy and expensive. And what's worse, see those long screws? They're in compression. They're being squeezed. That creates a huge risk that they'll buckle, which really limits how much force this press can handle. It's just not a great design. Now check out the design on the right. See that force flow loop? It's tiny.
It's small and efficient and completely contained inside the main mechanism. That big outer frame, it's not carrying any of the main load, so it can be way lighter. And here's the kicker. The long screws are now in tension. They're being stretched. There's zero risk of buckling, which means this press can handle a much higher load. It's just a smarter, more elegant design, and force flow shows you why in a split second.
So force flow is this amazing visual shortcut for judging a design. But what's really cool is that you can take this visual idea and turn it into a tool for doing actual calculations, like figuring out how much a part is going to bend or stretch.
And the way we do that is by turning our force flow diagram into what's called a spring network model. The big idea here is that no part is perfectly rigid. Every component a force passes through, a bolt, a gasket, whatever, it compresses or stretches just a tiny amount. So basically, it acts like a really stiff spring.
Take these sealed tanks, for instance. When the pressure inside pushes up on the cover, that force has to go somewhere. It flows from the cover, through the gasket, into the bolts, and then back into the tank itself, making a nice little forced flow loop.
And this is where it gets clever. We can model the bolts as one set of springs and the gasket as another, much softer spring. And by thinking of it that way, as a network of springs, we can calculate exactly how that load gets shared between them, how much force is stretching the bolts versus how much is squishing the gasket. This turns a really complex interaction into a solvable problem, which is absolutely critical if you want to, say, prevent a leak.
So when you combine these two ideas, you've pretty much unlocked the engineer's way of seeing things. You can now break down the physical world around you into a bunch of clear, solvable problems.
So let's recap the two big tools in your new toolkit. First, you've got free body diagrams. They let you zoom in, isolate one single part, and see all the forces acting on it. Then, you've got the force flow concept. That lets you zoom out, trace the highway of forces through a whole system, and judge how good the design is at a glance.
And now for one final thought. Just look at the object closest to you right now. Maybe it's the chair you're in, or the desk your computer is on. Can you see it? Can you visualize that highway of force we talked about? Can you actually trace the flow of its weight from the very top, down through its structure all the way to the floor? Because now, you can. You've got the vision.